So good evening everyone. Welcome to the fifth live session for the course Geomorphic Processes, Landforms and Landscapes. Can someone just tell me if whether I'm audible? You can just put it in the chat box if okay. Thank you so much. Okay, so the course is taken by Professor Javedan Malik, who is from the Department of Earth Sciences, IIT Kanpur, and myself, Ananya P. Mukherjee. I am a PMRA fellow, a PhD student from the Department of Earth Sciences, IIT Kanpur. So until last session, we learnt about the fluvial geomorphology. Okay, one of the most widespread changes that we see on the earth's surface is due to the action of rivers throughout their course. That is, we had learned about their youth stage, mature stage, old stage. Okay, so we learned how the river at different stages of its life, it shapes the different it forms different landscapes, it forms different landforms, how what is its erosional work, what is its depositional work, and how we can measure some of the things, some of the changes, and we try to understand how those changes kind of also affect the natural disasters like floods. This was something that we learned for the fluvial geomorphology part. So today we learn the another aspect of geomorphology, that is the tectonic geomorphology. So in basic words, tectonic geomorphology, in tectonic geomorphology you will understand the relation between tectonic and surface processes that shape the landscapes, form landforms, and these are usually uh, dependent on the active deformation or the active tectonics that are taking place, that it's ongoing right now or in the recent geological past it has been happening. And due to these this active deformation active deformation processes, a lot of landforms are seen. We also have some natural disasters which are associated with active tectonics or active deformation. And one of the most the common example for where you will see active tectonics happening is the Himalayas, as we know that it's active right now also. So tectonic geomorphology is going to help you understand the evolution of a landform because of the interaction between climatic, tectonic and surface processes. Okay, so all these have an interrelated role in transforming landforms at a place. So over here this is just an example of how you can use satellite data to kind of map the different tectonic geomorphology features, okay, geomorphic features, using the satellite data. So this is I think a LIDAR image, and this is an example from glacial moraines of Meeks Creek and McKinney Creek. So this is just an example of how you will find that due to active deformation, you will see a lot of different features that are associated with a certain landform. So one of the most common feature that we see associated with tectonics, geomorphic feature that is related to tectonics, would be an escarpment. Okay, what is an escarpment? It's the place where suddenly there is an elevation change, and it is usually like a cliff or a steep slope. So these you can find in different kinds of environments, settings. You can find this below a mountain range. You can find these near places where you have wave action. Okay, escarpment is anything that that in that area you will suddenly find an elevation change. Okay, Over here, the photo that is given, that is an example of the Niagara Falls. Okay, so you can see that there is a sharp elevation change over here, and due to this, waterfalls. Okay, we had learned about this even in fluvial geomorphology when we were talking about nick points. Now, nick points are usually along the longitudinal profile of a river, but escarpments are, they run across kilometers. Okay, they are a very large scale geomorphic feature. So, as we understood that escarpment is a feature that is going to separate two elevation levels. Okay. Now, it could be formed due to erosion work of the rivers, or whatever drainage system that we have. Escarpments could be formed because of the erosional work of that, or due to faulting structural action over there. We will learn a bit in detail about faulting in the coming slides. Okay, so this is one of the geomorphic feature that we use to study active deformation at any place, at places where you find such elevation changes. This is an example of a topographic map and how an escarpment might look on a topographic map. You can see over here that you can see that you can understand the relief. Okay, the relief that is okay, you can, yeah, you can understand that there is a relief over here, that there is a steep slope. Okay, so these are kind of, you can understand through contour maps also. What is a contour? Contour is the kind of a line that joins areas of equal elevation. Okay, so we see contours. Over here you can see a term called contour interval, that is between two contours the interval is 10 feet. Okay, so with the how closely contours are spaced together, how far they are spaced from each other, understanding that will give you the indication that whether that place has a steep slope or it has a gentle slope. So this is an example how topographic maps are used to study escarpments. You can see you can understand the shape of the escarpment over here. Okay, so topographic maps, satellite maps, these are very useful to study tectonic geomorphological features. Okay. Now we will learn about some of the other terminologies that are used, that we study, the features that we study to understand. So one of them is called the facets. So over here in the diagram you can see these triangular features. Okay, so these are called facets. They are triangular or polyhedral shapes which appear as hill slopes. Okay, that lie between two drainage systems. Now we know that most of the rivers, they originate in the mountainous regions. Okay, so the drainage system itself starts right from where they are originating and how they are coming down and cutting through the mountains in V-shaped valleys. Okay, so this place, okay, this is called a mountain front. Okay, this is called a mountain front, and these facets are usually they are a part of that mountain front. Okay, so the triangular facets that we are talking about, they could be an effect of both tectonic uplift and erosion by the drainage system. Over here you can see that when the say uplift and erosion is happening together. Okay, so maybe the rate of uplift is not as much, there could be a difference in the rate of the uplift and rate of the erosion. Okay, according to that, these triangular facets can form. Okay, which when you study these facets, with the help of topography maps or other kind of tools, you can understand whether this area is experiencing active faulting, or the facets that are being formed, or the erosional, or the the main agent that is forming the geomorphic features over here, that is due to the drainage system, or due to uplift or faulting. Okay, so you can understand that by studying these facets. So we can see that usually facets are formed due to normal faulting processes. We are going to understand what is normal faulting in the coming slides. Okay, and sometimes also we can see it in thrust faulting. Okay, normal faulting and thrust faulting are two types of faults at the fronts of the foothills. Okay, so as I said, this mountain front, this is the foothills. Okay, you can call it, you can think of it as the foothills, and then these are the plain lands. Okay, so this is your fault plane. Okay, this is your fault plane, and this entire place is your fault zone. Okay, so you can see that the triangular facets are meeting the plain lands at the fault zone over here, or you can say the foothills of the mountains. Okay, so this is one way that facets could be formed because of the interaction between the uplift and the normal faulting, and the second way is that due to the erosion work of the drainage basins. Okay, so over here you can see there are two drainage basins. Okay, and both of them are eroding, so this drainage divide between the two basins is going to stay elevated. Okay, because that's not where that is the kind of lateral limit of the erosion of that is done by a river. Okay, so because of that you will find that these triangular facets get developed because of that. Okay, now the significance of these facets and what do we interpret when we are studying these triangular features on the mountain front is that larger facets will imply that there is recurring faulting, and these are tectonically active fronts. Okay, so when this is tectonically active front, okay, so that means the uplift is going to be more than the incision of the incision done by the rivers. Okay, so the fronts are not very dissected. When we are talking about smaller facets, that means that these are not, these are less tectonically active. These are less tectonically active, and that means these have more dissected fronts. Okay, because when there is more erosion work, okay, or you can say when it is not tectonically active, the work done by the river is more. Okay, so you will find more smaller kind of drainages forming because the erosive power of the river is more than the tectonic uplift. So it will not incise, or like it will not deepen the valley as such, but it will start laterally forming more drainage basins. Okay, so this is how facets kind of help you in understanding the active tectonics that is happening in an area. Usually this is related to the mountain ranges. Over here, as we spoke of that, in mountainous landscapes, the organization of fluvial network is not random. Okay, so usually they are equidistantly spaced from each other. So, but and at the front of the mountain, you can see this equidistant spacing between the drainage basins, and this is going to be dependent on the distance between the main drainage divide and the front of the range. Okay, so as you can see, if the drainage divides are far from the front of the mountain range, you see that these are a bit wider. Okay, and these are wider valleys over here, but if it's closer to the mountain front over here, you can see that you will actually develop most smaller and steeper catchments. Okay, over here also you can see that if the height of the triangular facets, they are calling it ridges in this diagram. Okay, so because later on, like if you see from the front view, they will kind of appear like ridges only. Okay, like uneven tops, and it will look like a smaller mountain chain, which you can call a ridge also, in which is called a ridge. So if the height of the ridge is smaller, then you know that the drainage density has increased over here. Okay, so this is another aspect of tectonic geomorphic features, and also the interplay between the uplift that is happening in that area, and also the work done by the different drainage basins. This is actually an experimentally shown kind of the situation that happens when you have drainage basins developing, and they poured water, they sprinkled water in the experiment over like kind of tilted sediments. Okay, so and they have recreated a faulting over here. So over here also you can see that these triangular facets are forming over here, and these are the deposits due to the triangular facets getting eroded later on. So you can see that even with experimentally, it can be seen that the behavior or the working of the tectonics that we are seeing is similar. Over here you can see that these are places where they had poured water and they are forming smaller drainage basins over here. Okay, and then you will find this facets over here. You see that over here the drainage divides are almost the drainage basins are very close to each other. So you can say that they are forming very small triangular facet. So it will also give you an example of the drainage basin size and the shape and also the density. Okay, so it's important to study about these triangular facets that we see on the mountain front. Okay, at places where you have either active tectonics or fluvial work being carried. Now we come to some quantitative kind of analysis and understanding of the tectonic geomorphic features. So the first geomorphic index, okay, is the mountain front sinuosity index. We had learned about the sinuosity index even in the fluvial channel. Okay, so where we were trying to understand how curvy or how wiggly the path of the river channel is, okay, at one place, and this has direct implications to the kind of what the type of tectonics or the type of elevation changes, slope changes that is present over there. This was for the fluvial geomorphology. Okay, now for geomorphic index for the tectonic geomorphology, we have the mountain front sinuosity index. It is it's useful in understanding the tectonic activity of mountain fronts. It can be, as you can see the formula, there's LMF and the LS. Okay, so LMF is the total length of the mountain front. Okay, so you can see you will measure the total length of this mountain front surface and divide it by the straight line length. Okay, between like suppose you're only considering one section of the mountain front. Okay, so over there you are going to first measure the total mountain front length, and then you are going to divide it by the straight line length of that mountain front segment. Okay, so what does this index kind of imply? This is going to give you an understanding of the interaction between the tectonic signatures and the erosion work that is happening over there. Okay, see, erosion is normally happening anyway, because when there is uplift, okay, and you have an agent like a river coming down or maybe even wind, okay, so these agents, all of these agents are going to cause erosion. So the mountain front index, sinuosity index, is going to give you an idea about how, what sort of interaction is happening. Suppose if you have active fault segments, okay, so they will indicate lower SMF. Okay, so if you have active fault segments, you can understand that maybe the mountain front is going to be very sinuous. Okay, so it has a direct relation to the kind of the sinuosity of the mountain front. So so if you have a low SMF, okay, so that means your length of the mountain front is also going to be low, okay. And for, you know, for larger, if you take larger mountain straight line, okay, mountain front straight line length, okay, and you see that the curvature over there is not that much, okay, so it will give you low SMF values, okay, which will indicate that the most of the work that is happening geomorphologically speaking is due to the active fault segments that are present over there, okay. And whereas higher values of SMF is going to specify that that most of the work that is being carried on over there is due to the erosional processes. So now we learned about the kind of, you know, the quantitative, one of the quantitative tools to understand the interaction between tectonics and erosional processes that is shaping up an area. Now we come to the why are we studying this? Why do we need to calculate the mountain front sinuosity index? Why do we need to understand triangular facets? Okay, so all this is actually needed to understand active tectonics. Okay, tectonics have been have been happening since the, as we had learned in the first live session, I think, that Earth is around 4.6 billion years old, okay, and tectonics has been a part of the the Earth's surface processes. Tectonics has been shaping the Earth's surface since since the beginning, okay. What is the difference between that tectonics and the ongoing tectonics, you know, active tectonics? Active tectonics is kind of, you know, an age range. We define it by an age range, that is in present day or recent geological past, okay. If you remember, I had shown you the geological time scale, okay. So over there you have lots of eras, you have, you know, periods, and then you have epochs, okay. So according to those eras and periods and epochs, we consider only the say last few million years, okay. So million years like from the present day. So this, the any tectonics that has been happening in the past few million years, okay, and happening right now, we are going to consider that as active tectonics, okay. So we what we are going to understand from active tectonics is, again, it leads to the understanding of what sort of plate tectonics is happening over there in that area, okay. We try to understand any kind of recent seismic activities that is happening over there, what types of faults are faults are present over there, how are they moving, at what rate they are moving, whether they are going to be a risk in terms of earthquake monitoring, earthquake mitigation, okay. And most of the plate tectonics is related to continental margin areas, okay. So usually, even where you see mountain regions, these are usually the continental margin areas where you've had collisional activities, okay. So that is why we need to understand what are the processes that are involved in active tectonics, and also, you know, its effects on the landform changes, okay, changes in the landforms. So when we are talking about active tectonics, you can consider three different, you know, time frames for it. One is neotectonics, young tectonics, recent tectonism. So what is neotectonics? That is neogene quaternary tectonism. You can refer to the geological time scale and you can, you know, pinpoint exactly, you know, where your neotectonics will lie, okay. Then you have the young tectonics, that is the tectonic activity that prevailed during late Pleistocene and Holocene time. Okay, again Holocene, actually the current period that we are in, that is the Holocene period, okay. And recent tectonism would be last few thousand years, okay, or the upper Holocene. Upper means that is the most recent Holocene time, okay. now we understood that which time frame we are going to consider for the active tectonics. Okay, now we will understand what are the indicators of the active tectonics. Okay, when we are considering fluvial kind of action, to understand whether there is going to be any change in the pattern or in the way the river is flowing due to active tectonism. Okay, so we will try to understand how the meandering is happening, or if there is development in the braided pattern, or narrowing of channels, or development of ponds. All these, these changes or variations that we can see when we are considering the fluvial, the either the fluvial action or the tectonic related geomorphological features. Okay, so there are specific indicators that will tell you that there is active tectonism that is happening over there. Okay, so now we will go into the different kinds of indicators that we will see in both, just landforms that are associated with tectonics and landforms that are associated, or channel river channel patterns that are associated with fluvial action. So before we go forward, we will first try to understand the faults. Okay. Yeah. Okay. So what are faults? So to understand faults, you can first imagine, okay, suppose you have a piece of paper. Okay, if you have a piece of paper, you can, if you start pressing it together, you will see it's getting compressed. Okay, and if you start pulling it apart, you will see slowly after a time it will tear. Okay, so these are the two important stresses that play a role when we are considering lithospheric extension or compression. Okay, so suppose this is your rock. Okay, so you are trying to press it together. Okay, so obviously it's a rock is a solid, kind of a block. You cannot really, it will not accommodate the stress. Okay, it will not accommodate the stress and squeeze itself. Okay, so it will have a brittle response to that stress. So if this is, suppose your, a rock layer, okay, you're pressing it together, what will happen is the brittle reaction, and first there will be a fracture that is formed, and then there will be a displacement along that fracture. Okay, so because of you compressing it, one part of the layer will go up and one part will go down. Okay, similarly, if you kind of pull it apart, okay, you are extending it, it will develop a fracture over here and then it will break apart. Okay, now it is not going to be just like you breaking a chocolate or something. Okay, it will accommodate some part of the extension, okay, in between. Okay, this is a very simplistic understanding of what I mean to say, the driving forces that are creating faults on the earth surface. Hi Kuldeep, good evening. Yes, okay, so there are different kinds of faults, okay, and these faults are generated because of the response to the different kind of stresses. Okay, so over here we see there is a normal fault. Okay, I'll just take the no general general types of these faults. Okay, there are different orientations with respect to the fault plane. Okay, and you can kind of categorize these faults into more categories. So I will just take the general examples for you to understand the rest of the content that that I'm going to present. Okay, so first we will talk about the normal fault. Okay, so normal fault, what will happen is that this block has been pulled towards the left and this block has been pulled towards the right. Okay, so A normal fault is formed as a response to extension stresses, okay, tensional stresses. You can see that this block has moved forward, okay, this was a fracture that developed and you have a displacement along that fracture, okay. Now, when do we consider this as a normal fault? Okay, so if suppose this is your fault plane, okay, this entire surface is your fault plane, the rock block which is below the fault plane, okay, so if you are considering this as your fault plane, if it is below the fault plane it is called a footwall, and if it is above the fault plane, if the rock block is above the fault plane, it is called a hanging wall. Okay, you can just say the foot means under, hanging means top. Okay. Now for a normal fault, a foot wall is always going, the direction of the movement of the foot wall is always going to be upwards in respect to the hanging wall. Okay, or you can say that the hanging wall has moved down with respect to the foot wall. Okay, that is when you call it a normal fault, and normal fault is due to the extension. Okay, remember this. So, this is your normal fault. Now, what happens in a reverse fault? Reverse fault is when we are compressing, when the rock block over here has undergone compression. Okay, again a fracture forms, okay, and then you have a fault plane that is forming. Okay, again you see the fault plane is again kind of oriented in this manner, but now you will see that the hanging wall block has moved on top with respect to the foot wall. Okay, so the foot wall is still below the fault plane and hanging wall is still on top of the fault plane, but their movement directions with respect to each other is different when compared to the normal fault. Okay, so you have a normal fault, you have reverse fault. Reverse fault is when the rock blocks are undergoing compressional stresses, okay, and then you have the hanging wall moving on top. Then you have a strike slip fault. We had spoken about strike slip fault before also. What is strike slip fault? That the rock blocks are moving against each other, okay, past each other, against each other, okay. So there is no footwall or hanging wall in per se unless and until there is normal fault or reverse faulting involved. Okay, for strike slip there are two types of faults. Okay, if suppose you are the observer and the in front of you you are seeing a strike slip fault. Okay, if the left block appears to be moving towards you, okay, so if it is moving like this block is coming towards you, the left hand side, then it is called a left lateral for a strike slip fault. If the right hand side block is moving towards you, okay, with respect to the left block, okay, if the right hand block is appearing to be moving towards you, like when the displacement happens, then it is called a right lateral or dextral strike slip fault. Okay, left lateral is also called sinistral, and right lateral it is also called dextral. Okay, so you can just remember the top four faults for now. Okay, so you have normal, reverse, you have left lateral strike slip, and you have the right lateral strike slip. Okay, these are the common fault nomenclatures that we follow. Okay, most of the faults that are present in around the globe right now are some form of these only. Now there are other categorizations also based on the movement of the hanging wall with respect to the fault plane. Okay, so we will probably cover it later on if it is a part of this course. Okay, if you want to understand more, you can go to one of the live sessions that that I have taken for the earth sciences basic course. Okay, so if you want, you can learn about the faults even in that. Okay, so now we learned that faulting happens due to the stresses that are experienced by rocks at a place. Okay, now because of faults also, faulting mechanism is actually a part of the tectonics. Okay, plate tectonics causes faulting. Okay, so thrusting can be caused when you have convergent boundaries. Extension or normal faults are caused when there is divergent boundaries. Okay, we spoke about formation of the East African rift system. Okay, so that is rift is where formed when you have normal faulting at a place. Okay, and in Himalayas mostly you have thrust faults because it's a collisional boundary. Then you have San Andreas fault, which is a transform boundary, transform plate boundary. There you see strike slip faulting. Okay, so faulting is a part of plate tectonics, and due to faulting also you will find some geomorphic features that are developed. Okay, so in thrust fault setting you can see there are different kinds of uh, features over here. There are similar features for normal faulting and thrust faulting. Okay, but there would be slight difference in the say shape of it or the orientation of these. You can see over here that the fault scarp. Okay, so due wherever you have the fault scarp. Okay, now remember that this is the fault plane. Okay, I'll just draw it somewhere. Yeah, for a thrust fault, okay, suppose you consider this as a block. Okay, and this is your, so this is your fault plane. Okay, what is a fault scarp? Fault scarp is formed at this face. No, at any time whenever you see a normal fault, I'll show you an example of this. Okay, suppose you are seeing a normal fault from this angle. Okay, so from the front, okay, you're seeing, and this has moved on top and this has gone down. If you even reverse it, okay, if when you reverse it, this will still appear the same. Okay, where this has gone down and this has gone on top. This is still your foot wall and this is still your hanging wall. Okay, this is your foot wall, this is your hanging wall. No matter if you are observing from this side or you are observing from this side, the sense of the movement of the blocks of the footwall block and the hanging wall block remains the same. Okay, did that clear your doubt? I think Pooja asked
Yes,
it. I could not hear you, so if you can just put it in the chat box and I'll
yes,
move.
ma'am.
Okay, okay, okay.
Yes.
So, as I was telling, what is a fault scarp? Okay, okay. First, let us consider for a normal fault because it's easier to view. Because you have an exposed fault plane for a normal fault. Okay, so this region, okay, this surface where you will find that this part is kind of scraped, okay, because the wall because of the rock block has moved down. Okay, so this surface is called a fault scarp. Okay, now fault scarp is also the kind of surface where you will find those triangular facets that we spoke about. These form on fault scarps when we are considering a land, considering an area where most of the landform features are caused due to faulting. Okay. So, over here you can see that because this is a thrust fault, okay, this has moved on top, okay. So, the fault scarp is over here, and over here in normal fault you can see that the fault scarp, the orientation is over here, okay. It depends on where your hanging wall is, on where your foot wall is, okay. So, the foot wall is on this side, so you see that the scarps are also kind of oriented in that manner, okay. And then for strike slip faulting, you can hardly see any triangular facets as such forming, but what you will have sac pond, you have pressure ridges. Okay, so some of these features we will talk about in the coming slides. Otherwise, you can always Google some of these things if you are interested to know more about these geomorphic features that are related to faults. Okay, so for over here you can understand that due to the different types of faulting, okay, you will have similar or different geomorphic features, and their orientation and the way and their direction and their shape and sizes might differ with respect to the changing with respect to the variation in the faulting. Okay. Now we spoke about active tectonics, what sort of features are formed due to tectonics, active tectonics in areas. Okay, we spoke about faulting, and where faulting is an important mechanism of tectonics that we see across the globe. Now we try to understand how fluvial landforms or fluvial or the river course that we study to understand geomorphology better, how they react to active tectonics. Okay, so faulting is one of the most important active tectonic mechanism. Okay, and how faulting or uplift or kind of subsidence at any place. Okay, uh, uplift and subsidence is also related to faulting. Okay, so like when we are talking about a normal fault, okay, so suppose this area has moved on top, so this area will be uplifted. Okay, this area has moved down, so this will be subsided. Okay, so uplift and subsidence are also related to faulting. Okay, so active tectonics will have, you will have faulting, you will have uplift, you will have subsidence. Okay, and how these three or these kind of processes are going to change the fluvial patterns or channels, we are going to learn few of those over here. Okay, so the first thing that we had also learnt about this in the fluvial geomorphology part, the sinuosity of channels. Okay, so the sinuosity of channels is a direct indicator of the channel slope. Okay, of the channel stability, of the type of sediments that the channel is carrying. Okay, so the all these things are indicated by the different channel patterns. Okay, so channel pattern number 1 will be straight, then in 2 it is still straight. Okay, but due to the presence of both suspended and bed load. Okay, so the thalweg will be different. What is the thalweg? It's the the kind of if you take a cross section over here, it will appear something like this. Okay, so the water is flowing only in this region, and this area is your deposition or the bank side. Okay, then 3A will be a sinuous pattern, then 3B you will have meander, then 4 you have braided, and the last one would be anastomizing channel. Okay, so these variations could be due to different things, that is the slope gradient, the sediment load, the velocity of the flow, the stream power. Okay, and these are further related to water discharge, variation in water discharge, variation sediment load, presence of bedrock outcrops, human influences, tectonic influences. Okay, so in today's in this week's content, we are mostly going to focus on the tectonic influences. Okay, we had spoken about these in the previous, in the fluvial geomorphology part. Okay, so these have already been done. So now we will talk about the tectonic influences on the channel patterns. Okay, I had mentioned this in the fluvial geomorphology part, that when a stream is flowing, okay, when a stream is flowing, it will try to maintain the lowest energy state. Okay, that means it will try to maintain a constant gradient. Whenever there is a change in that, change in say slope or change in the water flow, okay, this gradient will shift, will be disturbed, and the channel will adjust itself in a way so that it can again attain that constant gradient, that low energy state. Okay. So, if a river bed is being steepened, okay, because of tilting, it will increase in sinuosity to gain that adjustment. And in reverse, if there is a reduction in the slope, there will be a reduction in sinuosity. Okay, so if there is a this area is uplift and this is downstream. Okay, this is your upstream and this is your downstream. Okay, if the upstream area is on top and the downstream area has tilted, okay, so this area you will see that the sinuosity has increased. Okay, so this is what we understand by the difference or the variation that the channel patterns that the channel pattern takes in, okay, whenever there is a difference in the slope of its upstream and downstream. Okay, so this graph will tell you that with increasing in slope, okay, so your sinuosity will increase up to a point. Okay, you can see over here, you will have straight, you have meandering, then you have braided. Okay, and the sinuosity increases up to a point, and after that it will not increase. Okay, it will start decreasing even with increasing in slope. Okay, this is again related to the channel slope stability, or at one point when there is kind of a lot of uplift at one place. Okay, so the water itself cannot flow with that much power, so mostly your most of the sediment load that starts getting deposited and the water flow reduces. Okay, that is why you get more of braided and these anastomizing streams over there. Okay, so this gives you an idea about how tectonics are having a control over your channel patterns. Okay, how your river is flowing, uh, what sort of erosional work and depositional work it is going to do. Okay, now we come to another aspect of fluvial anomalies due to reactive technique, that is aggradation and degradation. What is aggradation and degradation? Aggradation is increase in base level, whereas degradation is decrease in aggradation is increase in base level and degradation is decrease in base level. Base level as in uh, the we had spoken about it. The base level would be where your landform level is. Okay. So, if there is increasing in base level, it will be aggradation, where if there is decrease, then it will be degradation. Okay. It aggradation will happen when there are a lot of sediments. Okay, it will start getting deposited, whereas degradation usually happens where there is less sediment and the land over there will get degraded because there is more erosional work than depositional work, okay, or degradation. Then aggradation, as I mentioned, is associated with deposition of sediment, where degradation is associated with the erosion of the sediments. Okay. And aggradation happens when river has low kinetic energy. Okay, it has lot of sediments with it. It cannot flow with much velocity. Okay, so aggradation will happen at that point of time. Degradation will happen when your stream, your river has more energy. Okay, it can erode more powerfully because of that. Okay, so you can see that with respect to the factors that we are considering, aggradation and degradation will have different action on the landform formation. Okay, aggradation will build up at a place, build up the landforms. Degradation is going to erode the landform. Okay, so aggradation and degradation work by a river, it can get exchanged because of tectonics. Okay, so suppose your suppose your normal, like, present setting you have like this. Okay, so your aggradation will happen here, your degradation will happen here. Okay, suppose then there is an uplift at a place, okay, or this part has gone down. Okay, so firstly the flow direction might get changed. This is a very, kind of a drastic scenario. This does not happen, but I'm just trying to make you understand how it can get reversed, how it can get changed because of the tectonics that are happening. Okay, suppose this has subsided and this area subsided and this area got uplifted. Okay, so then this part will get degraded and this part will get aggraded. Okay, so this is a kind of relation between aggradation, degradation, and how fluvial landforms or geomorphic landforms can get changed because of these mechanisms. So as I explained, so when you this area, okay, there is a dome in between, okay, so this area will get aggraded, this area will get degraded, and again this area will get aggraded. Okay, because this area has got uplifted, there is a change in the base level. Okay, there is in over here the river will start incising more over here. Okay, so it will try to maintain its constant gradient. Okay, so it will start cutting down over there, the velocity or the kinetic energy will increase over there. So this area will get eroded, and these eroded, obviously with erosion the sediment load increases, and then later again at a lower slope area. Okay, so it will start depositing, because again because the sediment load has increased over here. Okay, as it's going down, the sediment load is trying to decrease the kinetic energy of the stream, and then this part will get deposited and this place will start getting aggraded. Okay, similarly in a fault, okay, at a place where you have fault, okay, you can see that this area is uplifted. Okay, by seeing this you can say, like, if you have understood the normal faulting and reverse faulting, you can say that this is a normal fault. Why is it a normal fault? Because this is the hanging wall, this is the foot wall. The foot wall is going on top compared to the hanging wall, and the hanging wall is moving down with respect to the foot wall. Okay, so with the hanging wall moving down, okay, so there is a decrease, there is an increase in the base level. Sorry, not increase. You can see that this part has gone down. Okay, this part has gone down. So this area is where your deposition will start happening. Okay, and because there is a change from the normal base level, okay, to the new base level. Okay, so this part will start getting eroded. Okay, now this is where we, when we are talking about the mountain fronts, okay, and the drainage divide, kind of drainage divide changing or triangular facets forming more. Okay, so all these this aggradation and degradation also control the formation of those triangular facets and escarpments and the other geomorphic features. Okay, so this aggradation and degradation is related to your tectonics and also the fluvial action of the rivers, and also we will see how this uplift or subsidence or faulting is going to have an effect on the channel patterns too. Okay, now before we understand what is anticlinal uplift and what is a synclinal uplift, I will just explain these terms. Okay, so these terms are related to folds. Okay, water folds. Now we understood that faulting is kind of like brittle response. Okay, now there is also a ductile response, okay, of rocks when stresses are acting on it. Okay, okay, so suppose we are considering this layered rock, okay, and we start squeezing it. The example that I gave, if you take a paper and you start pressing it, so you will see that folds are forming in the central part. The same thing happens over here, okay. Now assuming that these are rocks, okay, so you will form fold, okay. This is a ductile response, okay, and you will see folds. Now this crest, okay, this upward bending part is called the anticline, okay, and this is called a syncline, the trough part, okay. So the anticline moves upwards and the syncline moves downwards, okay. With increasing, okay, you will see that the anticline will rise higher and the syncline will go deeper, okay. So this is a basic understanding of what is anticline and syncline when related to folds. So when we are talking about anticlinal uplift, that means that this part is actually like this, okay. This is your anticline, and synclinal subsidence, that it will be like this, okay. So this is going down and this is going on top, okay. So the changes in the channel pattern would be caused, okay. Suppose there is a difference in the uplift of the anticline and the synclinal subsidence, okay. Why? Because the slope is going to change, okay. So these slopes are going to change if there is an uplift or there is more subsidence, okay. Over here this point is the anticlinal uplift, okay. Over here you have a reduction of slope, over here you have an increase in slope, okay. So increased slope is going to give you increase in sinuosity, okay. Now since this part has the slope has reduced over here, okay. So the water is the water flowing is lesser compared to the sediment load that it is carrying. It does not have much power in it to carry the sediment load because of the change in the slope, okay. So over here you will find your anastomizing channels, and over here you will see that the meandering has increased because of the increased slope, okay. Then you can see that with time it will again change to a sinuous or a braided channel, okay. And similarly in synclinal subsidence you can see, okay, this area is going down, okay. So this side slope is increasing and this side the slope is decreasing, okay. From here the slope change is different, okay. So over here the slope is increasing over here, so you have more sinuosity, okay. Then over here after a point of time, because the slope changes over here again, the water cannot carry the load, the water power is the power of the stream is lowered, okay. The sediment load has increased, so it will start depositing it over there, okay. So you will have anastomizing channel, okay. So this is how the channel patterns vary with respect to the uplift or subsidence that is happening in this area, okay. Aggradation and degradation, it's the same thing. Over here you have aggradation, over here you have degradation, okay. Over here you have degradation and you have your aggradation. If you compare this diagram to the diagram that we explained for aggradation and degradation part, okay. Now sometimes the entire channel pattern might not change, okay, but there would be some changes in the we learnt about point bars and other depositional features that occur within the stream itself, okay. There might be some changes in that, okay. So over here as you see, if there is an uplift, okay, and the profile of the river was like this, so you will have aggradation here, you have degradation here, and then you have aggradation here again. So aggradation, more sediments, you will see that there are more bars over here, okay. In degradation, erosional work is happening more, so you will find river terraces, okay. Then again aggradation, you will see that again there are more point bars, okay. Similarly, if there is subsidence, okay, so this part will be degraded, this will be aggregated, and this will be degraded again. Okay, so you can see degradation, aggradation, degradation. So when there is degradation, you can see that the water will flow through the point bars and the terraces. Okay, it will develop these features over here. In aggradation, there will be more bars. Okay, then again in degradation, the bars, it will have a similar pattern to the one before it was aggregating. Okay, so tectonics has an implication on the channel pattern and also the deposition patterns. Okay, erosional work and the depositional work. There is an interplay between all these factors. So, this is how we can study active tectonism at a place, trying to understand the sinuosity of the channels. Now, if you take out sinuosity index of these, fluvial channels that we are seeing, okay, you can understand where the tectonism is taking place, okay. And maybe with time to time calculations and kind of having a survey or with respect with satellite maps or something like that, you can understand the rate of change of these sinuosity of the channel patterns over here. You can then imply the rate of the active tectonism over there. Okay, so this is like the general understanding of how you can use these changes in fluvial channels with respect to the active tectonism at any place. So, we first spoke about one of like till now we have kind of spoke about geomorphic indices. There were few related to the fluvial geomorphology, and for tectonic geomorphology we have spoken about the mountain front sinuosity index. Okay, so now we come to the second geomorphic indices, which are related again to the fluvial uh, the drainage systems that are there with respect to the tectonic geomorphology also. Okay, so that is called stream length gradient index. Okay, so it is the study of the effect of the lithology that has on the rivers. Like it will depend on the resistance that the river faces while flowing through a certain lithology. Okay, so the suppose there is more hard rock terrain. Okay, so hard rock terrain, it is more difficult to cut through, more difficult to erode. Okay, and there is a place where you have low lesser resistant rocks or lesser resistant sediments. Okay, so the stream length gradient will be different for both these areas. Okay, so how do we calculate it? The formula is given here. SL is equals to DH by DL into the total length of the main stream. Okay, so DH by DL is the changes in the local slope of the channel segments. Okay, sorry, yeah, there's an issue with the slide change over here. Okay. So, and the L is the channel distance from where the channel midpoint of the river reach divides. Okay. So, suppose we are calculating for one certain river reach or the main stream. Okay. So, the L will be the distance from where the channel's midpoint is there. Okay. Now, what is the significance of SL? Okay, so if the stream is flowing over harder lithology or actively uplifting or actively tectonically active regions, it will have a higher SL value. Okay, higher SL value because the DH by DL part is going to be more. Also your river, the length might be more. Okay, so it is a direct it's a direct relation to your slope changes. Okay, and also and if the values are lower, okay, then it will have it will be flowing through softer rocks or slowly uplifting region or tectonically less active region. Okay, so like just in a general sense, you can assume that, you know, in mountainous regions, you will have higher SL values, and suppose you are in the plain regions, or you know, the foothill areas or the alluvial fan regions, so you will have a lower value of SL. Okay, so you can understand like that. So suppose over here, you know, you are given some values. You have 50 to 25 meters of del H, and then del L is your 1000 meters, L is 5000 meters. So you can calculate your SL value from this. Okay. The other geomorphic index that is going to, you know, help you understand, you know, ongoing tectonics or active tectonics at any place is the valley floor width to valley height ratio. Okay, so suppose this is your valley profile, okay, the diagram. Okay, so you calculate the ratio by your valley floor width, then the elevation of the left hand side and the right hand side of the valley, okay, and also the elevation of the valley floor. Okay, so just understanding, you know, just you know, seeing it, you can see that if your VF values are high, okay, so that means your valleys are broader. Okay, you can see that there is a relation with the valley width. If your width is high, okay, so that means it has more you know, wider shaped valleys, so it will have a higher valley floor width to valley height ratio. And if the valleys are narrower, okay, your valley the width is you know, smaller, your ratio is going to get smaller. Okay, so high VF values will be flat floored valleys and with low rapid uplift, and valley insertion rates of the river is also lower in these high ratio areas. Okay, if your ratio is low, that means the valleys are narrower. Okay, the uplift is more. Okay, your sides, the valley walls are rising rapidly, and your river is incising you know, more to keep in the, you know, to maintain its state. Okay, so V-shaped valleys will have, you know, values close to 1, and broad U-shaped valleys will have uh, higher values, higher than 1 point you know, ratio values. So mostly U-shaped values because of the, you know, more lateral erosion. Okay, so there is no incising, the valleys are not, you know, getting deeper, but it is getting wider because it has more lateral erosion work that is happening. Okay, for broad U-shaped valleys where your VF values are higher. Okay, so this is the significance of this index. Okay, how it will help you in understanding whether active tectonism is taking place or not. So if you have low VF values, okay, and your valleys are much narrower, okay, so it is V-shaped valleys, then you can say that tectonics is you know, playing a role right now in that area in you know, shaping the landforms over there. So now we learned about you know, how channel patterns are different, are differing, okay, due to tectonics. Okay, now we will try to understand how they are going to respond due to tectonic deformation. Okay, because of tectonic deformation, you will have change in the stream power that is you know, that is there for a river. Okay, so I will just zoom in a little over here. You can see. Okay. So, we are talking about the longitudinal profile deformation with respect to the channel pattern response. Okay. So, this is just, you know, the path that the river is following. Okay, you have uplift over here, you have faulting over here, you have subsidence over here. Okay. So, due to uplift, okay, this is a zone of uplift, there will be a deflection. Okay, then again the next deflection is going to be where your faulting is happening. Okay. Now, due to uplift, you will have aggradation here. you will have degradation here, okay, then you have aggradation here, then again there will be degradation here, and then there will be aggradation here. Okay, we already learned the relation between aggradation, degradation and the uplift and subsidence. Okay, then cross sectional adjustments. Okay, this area, okay, aggradation, there will be it will be more prone to overbank flooding, okay, or you will have a lake formation over here. Okay, that because where degradation is happening, okay, channel incision is going to increase. Okay, then again in between, when you have aggradation, you could have, you know, flooding in this area, or you have another swamp creation. Then again, where the faulting is happening, okay, across that fault zone, across that scarp, okay, suppose there is a scarp that is formed, you will have increased channel incision, okay, and then again you will have aggradation. Again in the aggradation part, you will have, you know, overbank flooding, because again over there more sediments are being formed, okay, and over there, you know, if there is a sudden increase in discharge over there, it since it's, you know, kind of in a flood bank region, it can you know, it can cause flooding in those areas. Okay, so and then if you compare the bed load the bed load grain size at the different you know, segments with respect to the tectonic slope variations, you can see that you will have finer grain in the aggradation part, you will have coarser grains in the degradation part. Okay, over here I will just mark it with A or D. Yes, do you have a question, Kuldeep? Okay, I think there was an issue. Okay, so I will just mark over here with A, D, A, okay, wherever you will have aggradation. So finer grain is aggradation, okay. Then your degradation will have coarser grains, then again you have aggradation, then over here you have degradation, and then you have aggradation again. Okay, so aggradation, degradation, the response, the channel response is going to be seen in the cross sectional adjustment of it, the bed load grain size that it has, okay, and the channel patterns that we had seen before. Okay, so tectonic slope adjustment is going to give rise to the phases of aggradation and degradation, and that in response will change your you know, response or the stream power of the channel. Okay, so wherever you have aggradation, your stream power is lower, okay, wherever your degradation is happening, your stream power is more. Okay, so this is the relationship between the different factors. Now suppose we spoke about the you know, stream power. Now we'll see how the channel patterns will change with respect to the tectonic slope variations. Okay, so again, to repeat, if we have, this is your sorry, yeah, so this area will have aggradation, then you have degradation, then you have aggradation again, over here degradation and aggradation again. Okay, so you can see where you have aggradation part, okay, change in slope, you will have a meandering reach, okay, then you have a braided reach in the this aggradation part, okay, then again where when the, you know, the slope is changing again, okay, over here you will have meandering again, then again over here you have braided reach, and then again it will go into meandering reach. Okay, so this is how it is going to change with respect. Suppose you have the meandering river in the start, okay, so this is how it is going to change. If you had a straight river in at the start, okay, you will see that with the change in slope you will have a higher sinuosity channel, okay, then again with the change in slope you will have a high sinuosity channel, okay, and then suppose you started with a, you know, braided river, say you, it is kind of a straight river, but it has a lot of sediment load also, okay, because of the uplift over here. Okay, so most of the aggradation will happen here. Then in degradation phase, it is going to convert into a meandering reach. Okay, then again the same thing over here. In aggradation, again it will become an anastomosing reach. Okay, and this entire area, it will be degrading. Okay, and suppose it was a braided river response. Okay, now if suppose the starting only it was braided, okay, then it will change into the braided channel, but with lower depositional or lower sediment load. Okay, lower depositional features, because it has lower sediment load. Okay, again it will extend up till here, but due to subsidence, again you will see that the bars, the depositional bars have increased in number. Okay, so this is the channel response to a kind of tectonic regime that is being happening. Or there, suppose there is uplift, and there is subsidence, then you have a faulting. Due to faulting, you have uplift and subsidence. So this is how the channels, river channels, are going to respond to tectonic deformation. There will be change in the stream power, due to which there will be change in the channel pattern and also the depositional pattern or the flooding pattern that we see. Okay, now this is an example of how, due to tectonic deformation, channel changes its kind of course. It will have implications in lateral migration and also in the sinuosity nature. Okay, you can see over here that this channel, okay, this channel is actually the older channel. Okay, with tectonic, active tectonism taking place. You can see that the sinuosity has increased over here. Okay, so this is the river channel in 2005. So from 1975 to 2005, okay, you can see that the channel pattern has changed. Okay, this has a direct correlation to the tectonics that has taken place over there. Okay, so this is an example how you can see that the channel response is going to change because of tectonic deformation ongoing in that place. Now there is another feature. Okay, so now we were talking that the stream is flowing through the region where the tectonic uplift has caused. Okay, suppose your stream is flowing through a region and the region laterally next to it has experience uplift or subsidence. Okay, suppose like it's flowing through the floodplain area. Okay, and the valleys are undergoing lateral shift tilting. Okay, lateral tilting. So what you will find is, it could be due to mountain building process, epiorogenic kind of processes, or you have asymmetric rifting. Asymmetric rifting is related to normal faulting. Okay, or tectonic loading by thrust. Okay, because of the thrust, a lot of deposition is happening at one place and the area is getting tilted. Okay, so these could be some of the reasons why you can have asymmetric tilting. Okay, the response that the river is going to have to such tilting is going to be a progressive unidirectional abandonment of the channels. Okay, suppose this was where the stream was flowing before. Okay, with tilting it is shifting. Okay, so there is an asymmetric river position shifting. Okay, and these are all previous meanders that have been later on cut off because the channel is migrating. Okay, so this is due to asymmetric tilting. You can see that the rocks have kind of tilted in this direction. Okay, so this is again a channel response to active tectonism that is happening, that is causing asymmetric tilting. Okay, over here also see this part has gone up and this part has gone down. Okay, so you can see that these are kind of evidences of abandoned channels. Okay, these were previously the meanders were kind of forming over here, but then they all got abandoned, they got cut off because the river channel is migrating. Okay, so there is another term for these channels. These are called paleo channels. Paleo channel study is another aspect of geomorphology. Okay, which helps you in understanding the past tectonics that have happened, or the active tectonics that is happening now, which has caused these paleo channels to be created. Okay, so either you will find meander loops, or you will have ponds that are still existing because of these this lateral migration, which is in response to uplift on one side of the river valley. This excuse me. Okay, so we learned about the channel responses, and we learned about some quantitative methods of understanding these the responses of geomorphic features to tectonism. Okay, so this is a summary of some of the geomorphic tectonics, geomorphic indices, sorry. So we learned about mountain front sinuosity, valley floor valley height ratio. We did not do drainage basin shape ratio till now, but we also did stream length gradient index. Okay, these have been taught to you, so these are the ones that I have covered. Now we come to another aspect of active tectonism, that is active faults. Okay, so as I had mentioned before, faulting is a very important mechanism of tectonics across the globe. So even for active tectonics, active faults are important for us to study. Active faults, usually it comprises of the fault line or the zone where the material has been crushed or eroded because of the displacement of the two rock walls or rock blocks. Okay, because of the movement between them, there is a zone that is formed along the fault line, that is that is part of the fault system. So over here you can see on the left part of the diagram, the stream is offset to the right. Okay, rightwards along the fault line. Okay, in the right part, the stream is abruptly, it's swerved rightwards. Okay, you can see that the stream is kind of moved this side. Okay, so the right side has come towards you. Then you can see that this has bent. Okay, this has bent in on the right block. Okay, then you have these scarps as we had spoken about. So this area, okay, this part is called the scarps. Okay, it's a planar face, and then there is a bench in front of it. Okay, so this actually scarp kind of defines your fault line. Okay, the top surface of the scarp, it is the fault line. Okay, and then there are few other features that kind of symbolizes the fault zone, that is your sag pond, pressure ridge and shutter ridge. Okay, so over here you can see these are represented in this diagram. The the photograph that you can see on the right hand side is an example of how the fault scarp appears. Okay, so this entire surface is called the fault scarp. Okay, so this is your fault line. You can see that it has also got folded. So just by seeing it, you can see that like there have been two kind of directional forces that have acted. Okay, so this has gone down, sorry, this part has gone up and this part has gone down. Okay, so there was kind of lateral stresses also, and there have been stresses like this which has caused the folding in this manner. Okay, so these examples are also seen in the world, and over here you can understand these fault scarp better with this diagram. Okay, and there are few other features also which are you know uh, which occur with respect to fault topography. You have fault scarp, you have folded surfaces, you have drag folds. Okay, so these are some of the features that if you see them, okay, you can kind of signify that this area is experiencing faulting in the current at the current scenario. Okay, so active faults, it's important for us to study, as we said before, because of, to understand the geomorphological features that are present over there. Also due to the risk of, earthquakes that could take place in such active tectonic areas, like tectonically active areas. Okay, so as an example, as I even mentioned before, Himalaya is a region where active tectonics is happening. Okay, and you have active faults in the Himalayan region. Okay, yeah. So you can see that these MFT, JMT, MBT, MCT, these are actually thrust faults. Okay, thrust faults was what? Where the hanging wall is moving upwards with respect to the footwall. Okay, this is a thrust fault. Okay, so the growth of Himalayan, these faults is actually because of the, kind of, yes, thrust faults are reverse faults. Okay, reverse faults when this angle, okay, when the reverse fault is occurring at low angles, okay, these are called thrust faults. Okay, the slopes are very gentle of the fault plane. The faults are said to be low angle reverse faults. Those are called thrust faults. Okay, thrust faults are a type of reverse faults. Okay, so these thrust systems, they are kind of, connected to each other. They have grown with time. Okay, and they are still active, and because of that, whatever features we see in Himalayas are, related to these thrust faults and their growth. Okay, so you can see that because of the presence of such thrust faults, this area is also, seismically very active. We know that, very recent earthquakes have taken place in these regions, and they actually are very, frequent in these areas. So that is why it's important for us to understand the features that are associated with active faults, and then studying about the active faults, so we can, kind of have earthquake risk hazard management, okay, which is important for us. See, earthquakes is a natural process, but its effects and repercussions in current, scenario is too much, because there is a lot of loss to property and life, which we try to avoid. Okay, so we have to study these, and because of that, it's important for us to understand the geomorphic landforms that are created due to active faults and active tectonism. So one of the features of, active tectonics with respect to faults, active faults, is the growth of faults. Okay, because of, say, this compressional stresses. Okay, smaller fault scarps are forming wherever, there are discontinuities. Okay, because of the compressional stresses, fractures are first formed. Okay, and with continuing, stress action, there will be displacement along these fractures, and then you will either have normal faulting or you will have reverse faulting, and then with respect to that, the fault scarps will form. Okay, host of fault scarps will form. Okay, with continued, tectonism, continued, stress action, there will be propagation of these, growth and propagation of these fault scarps. Okay, and with time, two neighboring fault scarps, MBT is main boundary thrust, GMT I don't recollect right now. It's something main thrust only. This is main central thrust, main boundary thrust, main Himalayan thrust, and this is with respect to the Tibetan plateau. Okay, so yeah, Jwalamukhi thrust. Thank you, Pravesh. Yeah. So the you can find these full forms on Google. It's easily available, or the different thrust faults that are there. Okay, so I did not remember the GMT, but this is main frontal thrust, main Himalayan thrust, main boundary thrust, or main central thrust. Okay. So as I said, with time these fault scarps are going to grow, okay, in size and also laterally, and with time these will get joined together. Okay, the fault scarps will join together, and now you see that the area, okay, which is experiencing faulting over there is has increased. It has become a bigger fault. Okay, so you are talking about this diagram. Yeah, so actually for Himalaya formation, before the Indian plate and the Eurasian plate collided, there was an ocean basin in between them. Okay, so which had sediments in it, okay, ocean sediments in it. When the collision happened, these sediments were brought to the surface, okay, and because of the collisional activity, there is tethys sediments. Yeah, this one, right? Oh, wait. There is a slight delay in the slide change. Are you talking about this one? Okay, so okay, so previously there were marine sediments which was part of the Tethys Ocean, okay, and when the collision happened, the ocean basin closed, and the sediments that were there, they were brought to the surface because of this collision, and because of the magnitude of this collision, there was difference in pressure, temperature, okay, and because of that these sediments, they got metamorphosed into rocks. Okay, so Himalaya is not made up of sedimentary rocks, it is made up of metamorphic rocks, but the origin of those metamorphic rocks are sediments, are the marine sediments that were part of the Tethys Ocean, and also some part of the Indian landmass, and also the Eurasian plate. Okay, is that understood? Like, did I answer the question that you asked? These colored are kind of as you can see, sub Himalayas, lesser Himalayas, and higher Himalayas. These colors are denoting the different Himalayan segments. They are not they don't have any implications on the type of sediments or type of rocks over there. Is that clear? Is that clear? Should I move ahead, or do you have any follow up questions for this? Who asked this? Yes, okay. Yeah. Okay, so the similar things happened in Himalaya. Okay, so no, they are not different age strata. They are the different segments of Himalayas itself. If you know, the Himalayas are classified into three. You have greater Himalayas, you have lesser Himalayas, and you have the Shivalik range. Okay, so that is what the colors signifying in that diagram. Okay, so similarly, as you know that the faults, okay, they grow and then they link and they will form bigger fault areas, fault line, fault zones. Okay, so the similar thing happens even in Himalayas, where firstly there were smaller thrust faults, okay, then later with time they joined together and formed a bigger fault area, and this again has an effect on the geomorphic land features that we see over there, and also affects the fluvial responses. Okay, this is another example where you can see the the faults are growing over here. Okay, So first you have isolated fault growth, then the isolated fault growth, there is, they are growing laterally and they start interacting and linking with each other, and with, kind of towards the ending of the, stress regime over there, you will see that you will find that the fault areas have increased, okay, and they form a one big fault zone. These are inactive, and these ones which have linked together and grown, they become active, okay, because they have increased in size and they have linked together. So the displacements are now easier across the entire fault zone, okay. Now one of the kind of features that we see that is responsible, that is resulting due to the active faults and fault growth and linkages is formation of piggyback basin or dunes, okay. So over here you can see that in the first, this area is your foreland topography, okay. So this is where your this is your mountain front, this area is your mountain front, and then this is your entire plain, the plain region, okay. You can see that these are the thrust faults over here. Yeah, I can just zoom in and show you, okay. So over here you can see that as and when the faults start propagating and they are growing, okay, they are moving, the thrust so the the hanging wall is moving, okay. So it is an ongoing process, and because of that you will see that there is change in the erosion work, there is change in the depositional work, okay. Over here first you had fan sediments, okay. Now because this fault is growing over here, okay, this fault is still growing, you see then suddenly there is a uplift over here, okay, because of this change in slope, okay. What will happen over here now? There will be aggradation over here, if you recollect what we had talked about, okay. So you will have aggradation over here, your stream power will reduce over there, okay. Your deposition will increase in this area, okay. And later on with time again some part of the stream might get across this, or maybe new streams are forming, okay. And now this area that has formed, okay, these are called your piggyback basins. This area is called the piggyback basin. Why is it called piggyback? Piggyback basin is that you ride, you ride on somebody's back. So the piggyback basin is actually riding on one of the thrust thrust blocks. That is, it is called piggyback basins or dunes for the when considered with respect to Himalayas, okay. Then you see with time this area is still getting uplifted, okay, because another fault has generated over here, okay. Now this itself is one drainage basin, okay, and now this is another drainage basin that is formed here, okay. So this is how active faults, active tectonics are going to create new features. They are going to create, they might create new drainage basins, and it will be different from the one that was flowing beforehand also, okay. So piggyback basins are types of foreland basins that are forming on top of a thrust sheet, and it kind of rides with that thrust sheet, okay. So because this part has now become a different drainage basin, and this is the new fault, okay, and this fault is still growing, okay. So now this will become active again, it's a new fault and it will become active, and it will start affecting the older thrust block, okay. This is your older thrust block. So piggyback basins are an example are a geomorphic feature that is created due to active tectonics in one region. Okay, another feature that we see which is related to active tectonics and how fluvial channels are caused to change their direction of flow is called paleo wind gaps. Okay, suppose this was your original slope. Okay, your stream was flowing in this direction. Okay, this is your high ground. With time, okay, with sudden uplift in this region, okay, so you see that this area has got elevated. Okay, and as you remember, this will be your aggradation, this will be your degradation, this will be aggradation again. Okay, but slowly with time, okay, this the stream cannot carry forward anymore. Okay, and then there is a break. Okay, so this part is called a wind gap, and you can see that because of that this river will start flow, this stream will start flowing from this side and this will start flowing on this side. So the flow direction has changed. Okay, so this place where you find that the current, the direction of the flow changes is called a wind gap. And why do we know that the flow direction has changed? Because the previous lithology that was present here, it still has the imprints of the older current directions. Okay, you can see over here the feature that has formed over there has an imprint of the older current directions. Okay, so the due to the uplift, the stream was forced to you know change its flow direction. Okay, so this is another kind of feature that you see because of active tectonics, which changes the way fluvial channel will respond. So that is it for today's week. Hopefully this content will help you in solving assignment problems and also understanding any part that you did not understand during your in the weekly content. If anybody has any question regarding today's content, you can go ahead and ask now. Okay, so if nobody has any questions, as usual, I will upload the recording of this lecture on YouTube
Okay,
by
ma'am.
tonight or hopefully by tomorrow morning. You can go through it again, and also the Google slides will be updated with the new slides. And the links are given in the NPTEL, the window in the resources, the resources tabs at the last. I think it's the last option, problem solving sessions. So you can get it over there, or if you have already subscribed to my channel, so you will get the notification on that too about the recording. So if anybody has
Ma'am,
anything, yes.
ma'am, can we get these slides in PDF form so that we can anytime access them? I mean, in a
Uh,
PDF form.
See, the thing is actually the NPTEL requests us to give it in the Google Slides form, but I think when you go to Google Slides, you can download the entire thing in PDF format.
Oh, okay, ma'am.
Yeah, you can change the kind of the file format when you download, or you download into a PPT and then you can convert it into a PDF. The issue is
Ma'am,
that the NPTEL team requests us to upload it as a Google Doc slides.
oh, okay. Ma'am,
Yes.
uh, the whole topic, this topic, which is fluvial geomorphology, is kinda confusing and boring, a bit boring.
Okay.
And what is the next topic, ma'am?
Uh, I think we will be also studying about the aeolian geomorphology, that where the wind is kind of creating landforms. See,
Mm-hmm.
it might be a lengthy topic, fluvial one, but because most of the landforms that are created are by the fluvial the river systems, so that is why it's an important topic. It's a lengthy one, I know, but it
Yes,
has more significance when we are trying to understand geomorphology. So,
especially the drainage system.
yes, the drainage systems, yes. So, I think today will be the end. I am unsure about the next content. The week 7 content is live, I think. So,
Yes, yes.
yeah, hopefully it's a new one. I have not checked it till now, but hopefully it's a different agent now. We still have to study glacial and wind. So hopefully one of those will be,
So,
on.
ma'am, your slides are so good. I mean, easy to understand.
Okay, thank you so
And
much.
so, would it be enough for the exam for
I
our
think yes,
NPTEL?
with respect to the exam and the weekly content slides that are there, both of these together would be, I think, enough for your, exams. If any other resources are mentioned by the instructor, I think it's better to consult those two, because if it has been suggested by him, then it might be, used for your exam purposes.
Yeah, ma'am. Actually, I saw the Javed Malik sir's PDF, which is about 600 pages, and I mean, kind of lengthy. Uh,
Like the
and yeah,
weekly PDFs, or which PDFs are you talking about?
no, whole PDF.
Okay, the all the weekly lectures.
Yeah, ma'am. The
Okay,
total PDF.
okay, okay. See, most of the things that is there is, for to you to understand what he's trying to explain. Okay, so there are a lot of slides, like there are a lot of pages where you will find, big photos, or
Diagrams.
satellite
Yeah.
images. So those things are for your understanding, but the rest of the things are your content, which is going to help you, like the written part of it. So even though if it's very lengthy, I think you will have to kind of summarize the content or by yourself. You can use the weekly content that is given. I try to summarize them, so you can correlate with your weekly content and see, and then make your own notes as per that.
Oh, sure, ma'am.
Okay. Anything else? Anybody has any other doubts? Okay, so if nobody has any doubts, I'll end the session for today. The video will be uploaded on YouTube. If you have any queries, you can ask in the comment section, or you can post a question in the discussion forum, and either me or the TA or another TA of the course will get back to you with clarification. So, thank you so much for joining, and hopefully I'll see you all again in the next week's live session. Thank you.